Hello everyone! In my last video I discussed a classic design for an analog oscillator. Today I'm going to take a closer look at DCOs, digitally controlled oscillators. You can find DCOs in synthesizers from the early 80s and replaced classic analog oscillators. We will see how they work and which problems need to be solved when building one. Alright, let's get started. So alright, let's take a look at the schematics. So this is a design which is heavily based on the Roland Juno DCOs, so the old Junos from the early 80s. What you see here, this is basically the oscillator core. So if you watched my last video on the analog oscillators, this looks very much alike. Here the difference, so this looks much simpler. The difference here is that you don't have a comparator like in this design to reset the oscillator, but there is a reset signal coming from a microcontroller. So basically this is connected to a pin of a microcontroller, and when the pin is going up here, so this is here basically detecting the edge when this goes up and is resetting this capacitor here. So this is actually quite simple. So basically you need a very precise reset signal which is coming here from the microcontroller, and then you would have here the expected frequency. So the basic idea is so a microcontroller usually runs at a fixed speed in the megahertz range or something, and basically the frequency here is derived from that clock cycle. So this makes it very precise, and this is why this is used in a design like that. So you don't have issues like in the analog design with temperature changes and so on, component tolerances and something like that. So this is something you won't have here. So this oscillator is very precise. But you would say, okay, this is super nice, but it's actually not that simple, because you have this precise frequency here, but when you take a closer look, so you also have here, this is charged, so you also have these this source signal, but the problem is that when you change the frequency of the reset signal, the time you have to charge the capacitor changes, and that means in the end that the amplitude is changing of the oscillator. So if you have more time, the amplitude is higher. If you have high frequencies, then the amplitude is basically is lower. So this is something we don't want, and this is something we need to adjust. So what you see here is basically, here is so dependent on the frequency, we do some adjustment on how much charge is going into the capacitor. So there are designs that use digital to analog converter here to adjust for the amplitudes. What I used in this design, so this is a PWM signal which is going through a filter. So the PWM signal, this is basically something like this. And this is afterwards, here is a filter, and this smoothens this out. So this basically means dependent on the pulse width, I get a different voltage. So this would here, this is very much alike. So this would basically result in something like this. If you have something like where the highs are very low and basically something like this, then this would result after the filter in something like this, and so on. So this is basically an easy way to get the voltage for adjusting for the amplitude. So this works very well actually. So this doesn't need to be super precise here. So what our human ear is good in is to distinct frequencies, but what we are not very good in is to distinct loudness or amplitude. So this is a fair, reasonable approach to tackle this problem. There are also designs from the early 80s where you have basically just an electronical switch which is changing between 3 different voltages or something like this. So very, very simple approaches are also possible here. Yeah, so and what this means, there is basically, so what we had last time, so there is like a source signal coming out of here with hopefully an even amplitude. And also we had this in the last video. So we need to buffer this so the charge is not breaking down here. So this is just a ramp signal, and this is here removing the DC offset, and this is here for the pulse signal. So this is just a comparator, basically, yeah, where you can change the pulse with an external control voltage here. Yeah, so this is all the same to the analog oscillator. So what I used for this design here, this is actually one of my more popular designs, which I never made a video of. So this is the DCO design I used in my very first video in the PolyKit 6 in the polysynths I built. So this is the design I used in there. So on my GitHub here there is a design for basically a 6-voice polyphonic oscillator, which is controlled by one Raspberry Pi Pico. So basically I use more or less all the I/O pins of the Pico to control 6 of these oscillators. And this works very good. So this is very precise. I used the Raspberry Pi Pico has a nice feature which is PIO, so programmable I/O pins. So basically you have a state machine which can be programmed in assembly language, and I use this to very precise control this reset signal here, and so this is a very precise oscillator. This works very well. And PWM, so this is something that the Pico offers. This is something I just control by software in the end. So this is a design which works very well, and yeah, let's check it out if you're interested here. This is all on my GitHub, also the software. Yeah, the software allows MIDI control of this, so I thought there's no need to go basically from analog to digital to analog again. So this is basically a MIDI controlled 6-voice DCO. Yeah, check out my GitHub. Everything is there. Also the software, if you're interested in. So also if you're interested in basically a rundown on the software side for this, yeah, maybe write in the comments, so I can maybe also make a video on this. So I think that's it for today. So we saw why this is so precise. So the whole design is much simpler than the classic oscillator design. So this needs a lot less components. Of course, you have the microcontroller here as well, and we also saw why we need to adjust the amplitude here, why this is a problem. Alright, that's all for today. You can support my projects on Patreon and make more videos like this possible. Alright, thanks for watching. See you next time, and bye for now.